that any homomorphic image of a finitely generated module is also finitely generated. Every finitely generated module is also finitely generated. We mean by finitely generated means we say that M is a, first of all, M is a module over a ring R, where R is a commutative ring with unity. If every element of M is of the form A1 x1 plus A2 x2 plus and so on plus AN xn, that is the linear combination of elements of X, then we say that M is finitely generated. So what do you mean by homomorphic image? If F is a mapping from a non-empty set G to G dash, then we say that F of G is the homomorphic image. So we prove that any homomorphic image of a finitely generated module is also finitely generated. How do we prove? Let capital M be a finitely generated module over a ring R. Let capital M be a finitely generated module over a ring R. That means you have AI, every element. Suppose if you take M belongs to M, M is of the form A1 x1 plus A2 x2, so on plus AN xn, for xi belongs to X and AI belongs to R. What is R? R is a commutative ring with unity. Now we prove that every homomorphic image of a finitely generated module is also finitely generated. Let F from M to N be a mapping. F from M to N, where N is any R module. Let F from M to N be a epimorphism. Epimorphism means it is onto homomorphism. Let X be a finite subset of X in M. We say that X is generated. X generates M. If every element of M can be expressed as linear combination of elements of X, we say that X generates M. Then, because F from M to N is a mapping and X is finite, means you have F of X also is, whenever X is finite, F of X is also finite. Now tell me what is Y. If Y is equal to F of X, then epimorphism means onto homomorphism. That means for every X belongs to M, there exists Y belongs to N such that Y is equal to F of X. That is F of sigma AI Xi for I is equal to 1 to N. As the F is a homomorphism, actually, in fact, this is F of A1 x1 plus A2 x2 so on plus AN xn. Means you have A1 F of x1 plus A2 F of x2 plus and so on plus AN F of xn. This is sigma I is equal to 1 to n or some j is equal to 1 to n aj f of x. That means which is a linear combination of elements of n. That means n is generated by, that is n is generated by f of x, or n is finitely generated. Because f from, we have taken that f is a homomorphism from m to n. Okay. So if x is any subset of m, then f of x will be subset of n. So n is the homomorphic image of m. So m is a finitely generated module and n is a homomorphic image of m. Therefore, every homomorphic image of finitely generated module is also finitely generated. And also, let us have some notations. Let n alpha is equal to, consider the class of all modules n alpha such that alpha belongs to delta is a class of submodules. Class of submodules of a module m. Of a module m. Then how you define sigma n alpha is the set of all x1 plus x2 so on plus xn such that each xi belongs to n alpha I. We take this class. This is again a submodule, which is again a submodule of m, and we know that it is the smallest submodule of m containing union alpha belongs to delta n alpha. Students, more or less, this is also like vector spaces. In vector spaces, we know that the set of all linear combination, that is the span, linear span. Linear span is the smallest subspace containing S. L of S is S. Here also, n alpha is submodule. If you take the class of all submodules, it is the smallest submodule of M containing union alpha belongs to delta n alpha. Now, next theorem says that let capital M be a module over a ring R. Module over a ring. Then the following are equivalent. Without knowledge of injective modules and finitely generated modules, you cannot prove a 9 lemma, 5 lemma. The following are equivalent. What are they? First one, capital M is finitely generated. What do you mean? When do you say that M is finitely generated? If every element of M is of the form A1 x1 plus A2 x2 so on An xn. And the second one, if n alpha belongs to delta is a class of submodules of M such that sigma alpha belongs to delta n alpha is M. Then there exists a subset F of delta such that sigma alpha belongs to F, n alpha is also M. And the third one, if M alpha is a class of R modules and F alpha is a mapping from capital M alpha to M or homomorphisms. Homomorphisms such that sigma F alpha M alpha is equal to M, then there exists sigma alpha belongs to F such that F alpha M alpha is M. The same thing holds for N also. And the fourth one, if M alpha belongs to delta is a class of R modules and M is a homomorphic image. M is a homomorphic image of M1 direct sum, M1 plus M2, so on, which can be written as direct sum of alpha belongs to delta M alpha. Then for any subset F also, F of delta, you have direct sum of F alpha belongs to F, direct sum of alpha belongs to F M. So all this you can prove easily by making use of homomorphism concept. So just you give one reading to the proof of this theorem. Once you know what are the major points in this theorem, just listen here. See, whenever M is finitely generated, then if N alpha is a class such that sigma alpha belongs to delta N alpha is M, the same equality holds for its subset also. And the same concepts holds for its homomorphic image also. Here, F alpha is a homomorphism, means homomorphism from M alpha to M, such that F alpha, sigma F alpha M alpha is equal to M. Then the same thing holds for a subset, its subset F also. Now, next important theorem is which says that M1, M2, etc., Mn be modules over a ring R. Modules over a ring R, and capital M is equal to M1 join, M2 join, so on join Mn with the direct sum. With the direct sum of Mi. Then M is finitely generated. M is finitely generated if and only if each Mi is finitely generated. Each Mi is finitely generated. So M is finitely generated if and only if each Mi is finitely generated. Okay. So this is a very important theorem under these modules. See here, we know that each Mi is the submodule of M, and that any element of M can be uniquely written as x1 plus x2, so on. Xn belongs to Xn, with each Xi belongs to Mi. Now, what we will prove, if and only if, means you have to prove that prove the theorem in two parts. First one is suppose M is finitely generated. prove that each mi is finitely generated. And the second part, suppose each mi is finitely generated, prove that it's a direct sum. Whenever m1, m2, etc., mn are finitely generated, prove that their direct sum also is finitely generated. Proof. You can take each mi can be treated as, because why treated as a submodule? Because m1, m2, etc., mn, these are all these are all modules over a ring are treated as a submodule of m, and that any element of m can be, you know the meaning of direct sum, okay? Uniquely written as x1 plus x2 plus and so on plus xn for each xi belongs to m. Now suppose each mi is finitely generated. Suppose each mi is finitely generated. Each mi is finitely generated. Then for each I, what do you mean by this? Then for each I, you can have a subset xi of mi which generates mi. So this implies union I xi generates m. That means m is finitely generated. M is finitely generated. Now, conversely, suppose M is finitely generated. Conversely, suppose M is finitely generated. Suppose M is finitely generated. Then what we will prove? We prove that each mi is finitely, M is finitely generated. We prove that each mi is finitely generated. What do you mean by M is finitely generated? Then there exists a subset Y of M such that your capital Y is equal to Y1, Y2, etc. YR of elements of M that generate M. That means each Yi can be written as sigma j is equal to 1 to n xij. Okay, where you have xij belongs to mj. That is, you have x1j, x2j, etc. xrj generate mj. So all these elements generate mj. So you take specific mj naught. Let us consider, or let us take specific mj naught. Then your x can be written as, because it is generated, each mj is generated. Generated means every element can be expressed as linear combination of elements of y. That is, you can write it as a1 y1 plus a2 y2 plus so on ar yr. This is sigma r is equal to 1 to n. I equal to I equal to 1 to r, sorry. ai yi. Again, what is this yi? Sigma I is equal to 1 to n ai. Each yi is sigma j is equal to 1 to n xij, which is sigma I equal to 1 to n, sigma j is equal to 1 to n ai xij. Okay. Therefore, which is the linear combination? Again, x is your x is also linear combination. Therefore, you get each mj naught is finitely generated. Because mj naught is arbitrary, you can say that m1, m2, etc. These are all finitely generated. Next one. Next one is the definition of free module. What do you mean by free module? Let the capital M be a module over a ring R. Capital M be a module over a ring R, and X is the subset of M. X is the subset of M. X is said to be a free generating set for M. Capital X is said to be a free generating set for M if every element of M can be uniquely written as or uniquely expressed as R1x1 plus R2x2, so on Rnxn. Here R1, R2, R3, etc. Rn. These are the elements of ring R. X1, X2, etc. Xn are elements of X. So if M has a free generating set, then if M has a free generating set, then M is said to be a free module. M is said to be a free module if it has a free generating set. What do you mean by free generating set? For elements of R and X, you have R1, X1, every element of M can be written as R1, X1 plus R2, X2, so on plus Rn, Xn. Then we say that M is said to be a free module. Generally, you know, if X1, X2, etc., Xn are there, and we are taking R is a commutative ring with unity, you can write it as 1 into X1 plus 1 into X2, so on, 1 into Xn. Then, so you can say that every ring R is a R module, free R module, with a singleton one as its generating set. And also the Cartesian product R power n, that is also a free module. You can give many examples like ring of polynomials. You can express it as R module, free R module. Next, let us discuss about projective modules. What do you mean by a projective module? Next topic is projective module. How you define a projective module? Let capital P and capital M be modules over a ring R. Okay. Module you define it is M plus is an abelian group, and we have seen the definition of a module. Let capital P and capital M be modules over a ring R. Let P and M be a modules over a ring R. Capital P is said to be projective relative to M. M. Or we say that M is projective. M is projective or P is said to be projective relative to M if for any epimorphism, the F of capital M into any R module, N, and for any homomorphism, G from P to N, there is homomorphism G bar from P to M such that F circle G bar is, this is the definition of projective module. Okay. Just to listen carefully. Yeah. Just let me explain with more clear explanation. How it will be? Yeah, this is your M. Here it is M and this is N. P is projective module. Here M to N is epimorphism. Epimorphism means onto homomorphism. And this is your G bar. And this is your G. So if P and M are modules, you have P and M are modules. You have to say P is said to be a projective module or M projective if for every or for any epimorphism F, onto F of M onto R module N. Here M is any module, N is R module. And for any homomorphism G from P to N, there exists F circle G bar is equal to G. So, which also you can prove by applying fundamental theorem of homomorphism also. Let P and M be R modules. Then P is M projective. If then P is M projective, if and only if for any submodule K of M, every homomorphism of P into quotient module M by K can be factored through the natural epimorphism of M onto M by K. This is another formulation of module. Next theorem is, let capital R be, let capital R be any ring with identity and M is R module. M is R module. Then every free R module, every free R module is M projective. Then every free R module is M projective. Suppose P is a R, suppose P is any free R module. Then you can have always your P is isomorphic to suitable Rx. Now Rx is the direct sum of class of Rx of R modules. What is Rx? Rx is the class of all Rx such that X belongs to X. This is the class of all R modules. And Rx is R. For all X belongs to X. So we prove that R is M projective. R is M projective. If you want to prove R is M projective, first you have to start with an epimorphism. Suppose F from M to N be an epimorphism where N is any R module. And you take G from R to N be a homomorphism. Then you have to find G bar such that F circle G bar is equal to G. F circle G bar is G. That's what you have to prove. And R is a ring with unit element. So what you will have, because F from M to N is on 2, you can have G of 1 belongs to N. For every G of N belongs to N, there exists X naught belongs to M such that F of X naught is equal to G of 1. Okay. Now define F from R to M by some, define HM. Define H from R to M by H from R to M by H of A is equal to AX naught. Then definitely H is a homomorphism. Then H is a homomorphism. Then find F circle H at A. This is F of H of A. This is F of AX naught. This is A into F of X naught. F of X naught ante entama G of 1. A into G of 1. A into G of 1 which is equal to G also homomorphism, no? G in A into 1 which is G of A. What do you mean by that? You found F of F circle H is G. Therefore, you have R is M projective. R is M projective. And the next one, let P and capital M be OR modules. P and capital M be OR modules. And suppose P is M projective. Always you have to remember, when you say that P is M projective, for every we say that P is M projective if for every epimorphism F of M, for every epimorphism F of M into any R module N, and see one onto homomorphism and homomorphism, there exists another homomorphism such that F circle G bar is equal to G. Okay. So now let P and M be R modules, and suppose P is M projective. Then for any submodule K of M, P is K projective also. P is K projective and M by K is projective. M by K projective. This you can prove by using the making use of definitions of homomorphisms. By definitions of homomorphisms, easily you can prove this theorem. And next definition is an R module. An R module P is said to be projective if it is M projective. If it is M projective for all R modules M. For all R modules M, if it is M projective. R module P is said to be projective module. R module P is said to be projective module if it is M projective for all R modules M. You focus on the definitions. Once you are clear with the definitions, then you can prove easily the theorems. An R module P is projective if and only if it is isomorphic to a direct summand of free R module. Now let us discuss about injective module. What do you mean by injective module? Instead of epimorphism, if you take monomorphism, then we will get injective module. See, let I and M be R modules. Capital I and M be R modules. Then capital I is said to be injecting relative to M. injective relative to M if for any monomorphism. What is monomorphism? 1-1 homomorphism. For any monomorphism F of a R module N into M, and for any homomorphism G of N into I, as usual. In place of epimorphism, in the projective module, you have taken epimorphism. Injective modules, you take monomorphism. You replace epimorphism with monomorphism. And for any homomorphism G of N into I, there is a homomorphism H from M to I such that H circle F is equal to G. Same. So this is known as injective module. That means how you explain this? So here there will be N. Here it is M. This is L. Sir. I. F is a monomorphism from N to M. N is G is from L. Then H is from M to I. So this is about injective modules. Now we will see when a module will become injective module. Let capital I and capital M be or modules. Then I is M injective. M injective if and only if free monomorphism for every morphism of every monomorphism of a submodule of M into I can be extended up to morphism of M into I. Now, an module, an R module is said to be injective if it is M injective. If it is M in every R module M. For every R module M, have an R module and it to be injective if it is injective. So now next theorem is important one. This one is the Bayes criterion, where BAER, where criterion or the injective test in test lemma. Which states that suppose always ring means the commutative ring with one element and I is an R. Okay, then you have which states that commutative ring with the unity, commutative ring with unity and I an R module. Then first one, the following are equivalent. You have I is injective. I is injective. Second one, I R is and third one, for any ideal J of R and for any R homomorphism G from J to I, there is an element X such that G of A is equal to AX for all A belongs to J. So these three are equivalent. In the next class, we prove tensor functions, 9 lemma, 5 lemma and all we will prove. So today we have discussed about R modules, projective modules and injective modules and their properties.